Hi, Koshika. Will wait for 2 3 minutes so that other question also join. Hello, Koshika. Are you there?
Yes, sir. Yes, sir, I'm there.
Yeah. Okay. So we'll start. Others will join. So I will be going to first revise the
Okay,
second week work, and then we'll discuss about the questions. Is
okay,
it
sir.
fine?
Okay, sir.
Okay. Hello, Apeksha. Hello, Apeksha. Are you here? Apeksha. So I request you, both of you can ask questions because I will be going to revise that. So if you want to ask anything, you can ask. Okay. So week two discussion started with the some usual definitions. So that is uh, grafting density. Should change the color of the pen. Grafting density, which means the number of molecules grafted on grafted on a colloidal particle divided by the area. in total area of the particle. So basically, this has to be find out, and when we have this colloidal particle, there is some grafting molecules. So what we usually do is we should do PGA, as that was also discussed in the lecture, that is thermogravimetric analysis. And find out the weight of the grafting molecules. So grafting density can be defined as mg by mw into na by nf divided by the area. Okay, so that is the definition that is used for the grafting density. Then we have a surface charge density. I think we have discussed one numerical in the last class on this. So surface charge density is the charge induced on a colloidal particle. So that is sigma, that is q. So that is on surface charge density. Okay, so here n is the Avogadro number. Then he discussed something about surface roughness, but the main thing that is discussed is the Brownian motion. The majority of the week 2 lectures are on Brownian motion. Any doubt till now, Kaushika, in any of the things that of these definitions?
No, sir. Actually, I have not seen all the videos of week two, so I have seen only little. I have not completed it.
Okay, but what we have discussed, is there any doubt in that?
Sir, we have now you said about the crafting density, that part, which is already said it in the week one lecture, no, sir?
Yeah.
Yeah, that's
Yeah, that is there in the week 1 lecture.
yeah,
Uh,
yes, sir.
it's just a bit revision on it. Sir, so the second week lecture is mostly on the Brownian motion. So can you tell what is Brownian motion?
The Brownian motion, when the particles in the colloidal state, when the light, some I forgot some Neil relaxation, these things.
What?
It's confused. Neil relaxation and Brownian motion, I got confused which one is which. So I have not seen the video fully. I have to watch the week 2 weeks lectures.
Okay, no issues. Debaran, do you know what is Brownian motion?
Yes, sir. A bit. Like it's like when like small atoms and molecules like move in a haphazard state.
Yeah, tell.
Yeah, move in a like haphazard state, and so that motion when it's like observed in under like an apparatus like like a microscope, which is of higher power. And yeah.
So basically, I am telling you what. So Brownian motion is a random motion. So what you are saying haphazard. So that is random motion of particles suspended in a media. Medium can some sort of fluid. So those random fluctuations that particle is there. So that is called the Brownian motion. And this motion is essentially because of the thermal energy that the molecules that these particles are having. So Robert Brown was the scientist who observed this random motion of pollen grain. And why he is able to observe this kind of motion? Because the type of particle uh, doing Brownian motion is important. So I will be going to discuss about that. What is the particle that you know that the kind of particle should do the Brownian motion? So any question on this? This is the random motion. So the type of particle doing Brownian motion is actually important. Uh, some of the conditions on or the constraints on the type of particles includes first one is that they shouldn't be attract or repel each other nor stick haphazardly. So there shouldn't be any cluster formation. So you should be aware that the particle uh, that has to do the Brownian motion should not be, there shouldn't be any interaction between the particle. The particle should be as spherical as possible. Because Brownian motion, these experiments are used to calculate the diffusivity of the particles, and which can be found using the Stokes-Einstein theorem, and Stokes-Einstein theorem is worked well for the spherical particles only. So particles needed to be as spherical as possible. Thirdly, the particle, the density of the particle should be such that they float. Not so it should be of the equivalent of the dispersion media. The density of the particle needed to be closed to a dispersion media, so that neither they should sink nor they should float to the surface. So that is one of the important point. So these are the difficult constraints on the type of particles that is needed. Now after this, there is one more difficult constraint, that is the size of the particle. Particle should be small. As uh, bigger the particle, more it resisted, more it get resisted by the surrounding atoms or molecules. Being resisted means uh, they are decreasing its velocity. So, so Brownian motion is essentially used to calculate the diffusivity. And so, if this motion is slow, then it needs a weeks to get the data. At the same time, particle shouldn't be too small so that it move very fast and you are unable to track that particles. Okay. Also, the particle shouldn't be too small. So there is so, so small such that it would be impossible to track the particles. So these are the some of the essential constants on the particles that are doing the Brownian motion, and Robert Brown is the one who is able to found such a particle, and this is the particle that is pollen grain, which follow this kind of constraints, and that's why he was the first one who uh, come up who tell this that this is the Brownian motion. So Brownian motion is that the particle do a random motion in some suspending media, something like this. So some random motion is followed by the particle, and if we uh, put it in the grid, then we are able to find out the mean square displacement, that is MSD. So something like this, we have a grid, uniformly spaced grid. To track this particle, to find out the mean square displacement, and from that mean square displacement, using Langevin approach, we are able to call it using Langevin approach. We are able to correlate mean square displacement with the diffusivity. Okay, so that comes out to be x square, that is nothing but x at minus x, and that is equals to 2d dt. So d is the dimensional space. If the particle is moving in 2 dimensions, then d is 2 for 2d. If it is 1, then it is 1d, and so on and so forth. Any questions on this? So Brownian motion experiment is used. Okay, any others? So when we know the diffusivity, we are able to correlate it with, and we are able to find out the Avogadro number. So the pair in,
Yes.
hello, yeah. Any question?
No, sir. No, sir.
Okay. Any objection on what I had said just now?
No, sir. No, sir.
Okay, so how can we correlate this diffusivity with that of to find out the Avogadro number? So that is a Stokes-Einstein relation. Stokes-Einstein's relation. So that is d is equals to kbt by 6 pi mu r. R is the radius of the particle, and mu is the viscosity of the dispersion medium. And from here we know d, so we can find out what kb is. So when we know kb, we know what is Avogadro number using this relation. Okay. So this r is hmm, so I should put this r to be the radius. This r is the radius of the particle, or I can say this a. And this r is gas constant. So parent is able to calculate the issue. Parent is spelling should be correct. So that is so this is the sort of, we in general statistical mechanics we call it as random walk. So the particle is doing some random walk and we can find out its diffusivity. So we have discussed the constraint on the particles that can do Brownian motion and what is Brownian motion. Okay. So now what we will be going to discuss is how to choose correct particles. What is the thing that is, what are the things that are needed to know how to choose. So any idea about it? Any of anyone?
Sir,
That and one more point. So here what thermal energy I'm saying is so that is the thermal so this diffusion is coming because of this thermal energy, and the thermal energy is coming here. So that is kBT. So T is the temperature of this disperser. So that particle is having some kinetic energy, and that is, yeah. Now, Debran, you are saying something?
yeah, we can like you're asking like how to choose correct particles. So like
Yeah.
these things like viscosity, these should be minimum, like these parameters. So we can choose like according to that.
Uh,
Hello.
Hello.
So have you heard my point?
No, actually, can you repeat?
Oh, the things that you have written, like the
Yeah, yeah,
viscosity of the no, sir, the last page that you have wrote. Yeah.
yeah, yeah.
So
How to choose
here,
part?
yeah, like these things, like the viscosity of the dispersion medium and stuff, they should be like minimum for us to choose correct particles. Like different parameters, like we need to consider.
Yeah. So first point is that we should know what is the we should know the type of forces acting on the particles in the
Yes, sir.
dispersion. So that's why all these buoyancy that we have discussed and the so that it shouldn't fall and hydrodynamic forces. It should be managed in a way. So this is the hydrodynamic force that is coming from the hydrodynamic force. So all these things we should know a priori to choose the particle. So types of force acting on individual particle in the dispersion medium. Second point is that interaction force between particle. Okay. So so the forces that are acting on individual colloids includes the hydrodynamic force, so when a colloidal particle moves in a media, so it uh, so there is a force that is acting due to the viscosity of the fluid, and that is the viscous resistance that the particle is feeling, and that is what we call as hydrodynamic force or the viscous drag. This is also causes viscous drag. So that is F comes out to be 6 pi mu uh, r. So that is the radius of the particle into velocity. So this is the force. So that is the drag force. Second thing is the Brownian force. So that is defined as kBt by A. So each particle is colliding with another particle that is having a kinetic energy kBt. So this kBt by A is the force, that is the Brownian force. That is, then we have, so this force is arising due to the random collision of the particles. Random thermal collision of the particles, and those random thermal collision is because of their thermal energy. Uh, and this Brownian force is responsible for the Brownian motion. Okay, so this is that force that is responsible for the Brownian motion in the color, which is leads to a diffusive motion. So any question till now? Then we have force of gravity. So that is, we very well know what is that force of gravity is. So that is the buoyant force. So that is rho, density of the particle minus density of the suspending medium. I can call this as Vp minus rho s. And the volume of the particle, that is 4/3 pi a cube g. Okay, so this is the density of the suspending media. So for colloidal particles, the gravitational force is of the order of, for colloidal particles, gravitational force is of the order of Brownian forces. That's why it's particles are suspended in the medium. Another force is that is osmotic pressure force. So this is nothing but normal pressure force, that is and kVt. So each particle is colloiding with each other, they're creating some pressure in the media, and the total pressure is the total number of particles they into the total amount of energy on each particle, that is kVt. So that's why it's osmotic pressure force. Okay. So any doubt till now? Anything? Apeksha? Hello?
Yes, sir. No, sir.
Any doubt?
No, sir. No, sir.
Anything if you are unable to understand? Dipanvita?
Yes, sir.
Any doubt?
No, sir, I have no doubts.
Okay. Kaushika and Devaru?
No doubts,
No,
sir.
sir. No, sir.
No doubts.
Okay, so these are the forces. So while choosing the particle, we have discussed about the forces. Now we should discuss about the interactions between the two particles. Okay. So that is colloidal interaction. So the interaction between two particles includes, so when they have having a two particles. In the next week, we will be going to see these interaction in detail, but mostly when two particles are interacting, they are interacting by what's we called as VDW force, that is van der Waals force. And it is mainly attractive force. So when you see, this is the very popular curve. Okay, so this is the distance between the two particles. that is X nanometer, and this is phi into 10 to the 21 joule. So this is the energy uh, when two particles. So that is the interaction energy of the particles. So that's the minimum. This is the minimum energy that is needed. So there shouldn't be any. So the two particles are in equilibrium when they are having this minimum energy. This is the minimum energy well, and this is the distance. So this is part of attractive potential. So this comes from the attractive potential, which is long range in nature, and this is a repulsive, normally come from hard sphere model when two particles are very close to each other and then they are feeling a repulsion. Hard sphere model, and this hard sphere model is goes as r to the power minus 12, this goes as r to the power minus 6. So combination of these two, what we called as Lennard-Jones potential. So this can be defined as, this is the combination of attractive plus repulsive. So that is some constant. So here it's the distance, so that is x to the power minus 6. X to the power minus 12 minus beta x to the power minus 6. So in the next week, we will be going to see this in detail. So this is what we call as van der Waal interaction. There are other interactions also that are surface forces. So those surface forces interaction.
Sir, can I
Yeah.
ask a question? Sir, what it is written there in the y-axis 5 into 10 to the power 21?
Yeah. Joule. So this is unit is in joule. Any doubt?
No, sir.
Okay. So that is one of the force, that is one of the interaction between the two colloidal particles. Another interaction is comes from the surface forces. So the surface forces arises from the proximity of the colloidal surfaces. So that is when one surface is having one colloidal particle has some charge or some absorbed ions, then uh, it's sort of two charges. If you see, then they can attract or repel each other, depends on the nature of the charge of the two particles. These forces either stabilize the colloid or destabilize the colloids. That depends on the range of interaction. So this interaction arises from the proximity of the colloidal surfaces in colloidal dispersion. Okay, where the surface can be charged or having some adsorbed ions, maybe some having some surfactant at the interface. Surfactants, maybe some polymer drafting is there. All these leads to the surface interaction between two colloidal particles. Okay, then third one is depletion forces. So it arises from the soluble polymers or nanoparticles that lead to attraction so two colloidal particle try to attract, and then they are unable to access the space between the two because of some sort of disturbance, and we can say like you have a parallel plate cap two parallel uh, plate capacitor, and you put some dielectric media inside that, so it is some kind of depletion. So this depletion is because of this some instead of free space, there is some molecules are coming that are depleting the interaction between the two particles, so that are called as depletion forces. So this is all about the what we have discussed. Then the most of the part of the lecture comes on is on the dynamic and the static light scattering. So we have time. Yeah, we have time. So light scattering techniques. Any doubt in all of these interactions that we have discussed so far? Anything? Okay. So we have different kind of light scattering technique, that is dynamic light scattering, and we have static light scattering. So in case of dynamic light scattering, the fluctuations in light intensity is measured with the time. So the fluctuation in light intensity is measured with time. So this is already discussed in lecture, so I'm not going to discuss too much in detail of it. So that is dynamic, where we are observing with time. So that is dynamic, as the name suggests, and this is static, where we use the time average intensity of the density of a scattered light. So from these methods, we are able to capture the diffusivity or the effective diffusivity of the polydispersive medium. Dispersed medium. And in case of so when we know the diffusivity, we can calculate we are able to calculate the dynamic radius of the particle using Stokes Einstein's relation. So please let me know if you have any doubt in all of these. After that, I will be giving two numericals that will help you in solving the assignment problems for the week 2. So if you are having any doubt in any of this, what we have discussed till now, please let me know. Anything? Any doubt? Can you please unmute yourself because it's
No,
a
sir. No
session,
doubt.
shouldn't be.
Sir, can you go to the first page? I was not there while you were teaching the first page.
Okay. So this is already discussed in the week 1 lecture, so this is nothing new, but I have discussed this Brownian motion. So are you there when I have discussed Brownian motion?
Sir, I was in the 4th point when you were discussing.
Okay, okay. So I have discussed that Brownian motion. You know what Brownian motion is. That is the random motion of the particle suspended in a media. So they colloids with each other due to the thermal energy. So there is a thermal diffusion of the particles, which is causing this random motion. And the type of particle. So why Robert Brown is able to find out this, able to see this, because he is able to find out the correct particle that is. So he used the pollen grain, which sort of uh, uh, correct particle to capture the Brownian motion. So what are the constraints on this particle so that they shouldn't be attract or repel each other, and nor should it stick haphazardly to the walls or any of this media. Particle needed to be spherical as possible because we will be going to use the Stokes-Einstein's theorem to calculate the hydrodynamic radius or the other things. So that is valid for the spherical particles only. The density of the particle not valid actually work well for the spherical particle, and the density of the particle should be close to the density of the surrounding media, that is the dispersion media, so that it shouldn't be it should neither sink nor should float to the surface. And the size of the particle shouldn't be too large, too small, because if it is too big, then the velocity that the motion is very uh, slow, and you will not going to able to get the good data, that is the good mean square displacement. And if it is very small, then then the motion is very random, so it's very fast and you are unable to track that particle. So both shouldn't be there. Is it clear?
Yes, sir.
Okay. Anything else? So after that, I will be going to give a numerical to solve. So in dynamic light scattering, there is a relation discussed between, so that is, the intensity, and so we have a relation that is the second, we generally call it the the relation we can that relates the intensity. So this is the function that varies with time. That is the intensity that we have captured. So that is T I plus delta T divided by I. And it is correlated to the first kind, the function of first kind, that is 1 plus zeta G1 square, and this is what we called as machine cost. Okay. So this is the constant of the, so that depends on the equipment. And we know G1 of tau can be related to the diffusivity and time in experiments as when. So what we do is we have an intensity of light, so that is correlated in a way with this function as e to the power minus d u square t plus b. Okay, so that is for the monodisperse particle. If it is polydisperse particle, we integrate this because the particles are different, and we integrate it from unity, and we get this exponential of minus gamma bar minus gamma d gamma, where gamma is dq square. Okay, so this comes in the dynamic light scattering technique. So these are the functions that correlate intensity with the time. So we are relating time with the intensity. So we usually plot this G1 with time, and with this correlation we are able to get this constants, and we are able to get the diffusivity. So our aim here from the dynamic light scattering is to find out the diffusivity and so the hydrodynamic radius. Okay, so you need to use this relation to solve the numerical that I am giving. So the question is, I'm not going to the details of from where this function is coming, because it's a very introductory thing. There are details, but if we'll see after the solving the numerical. If anyone is interested, we'll look into it. Okay. So the question is, a dynamic light scattering experiment is carried out to measure the size of the mono-disperse particle undergoing Brownian motion in a colloidal dispersion. The viscosity of the dispersion media is 0.002 and density of dispersion media is 2000 kg per meter cube. The density of colloidal particle is per meter cube at a temperature of 27 degrees centigrade. The data obtained from DLS is S P square into 10 to the power minus 10, and that is function of second time that relates the intensity with the time. So that is 0.2. Zero 0.4 1.2, sorry, 1.3, 1.2, 1.2, 1.4, 1.2, 1.6, 2, 1.005, and that's it. So you have this data. You have to use, so you have to, so first question is find the diffusivity You need to find out the diffusivity. Second is second question is find the hydrodynamic radius. Then find the hydrodynamic force on a colloidal particle. Then find the gravity force. Then find out Brownian force. Okay, I hope all the data is there. So Seagat relationship is this. This is the Seagat relationship. Here D is the diffusivity. Sorry, it's so here it's Q is changed with S. So here I can also keep Q, that is Q. So that is Seagat relationship is this 1 plus and G1 is minus D Q squared D Q squared tau plus B. And for this case, zeta is 1. Okay. So I will be giving you some time. Is it, are you able to understand the question? Debaro,
Yes, sir.
are you able to understand the question?
Yes, sir.
Apeksha,
Yes, sir.
Dipanvita,
Yes, sir. But it will be
Kaushik,
difficult for me to solve.
what?
It will be difficult for me to solve, sir.
Yeah, but you can try. Anyway, I will be going to solve it, but you can try it. Kaushika, you can use some tools also, Excel or something.
Yes, sir. Question. I can understand the question, but I
Okay.
don't know how to solve. I will solve.
Yeah, you have a relationship, this,
Okay.
you have this data, you have to correlate and found this. And
Okay, sir.
if you find out the diffusivity, then other things are simple. Okay. So try this. I will be waiting for let's say 10 minutes, and after that we'll discuss it the step by step. Okay. Uh, in 10 minutes, we'll discuss the first part, and we'll give you other 5 minutes for other questions. So first part is the difficulty. If you get the first part, then other things you will get it easily. So you should be knowing this formula, that is secret relationship, in order to get this diffusivity. So here it is tau actually. Okay, this should be G. Okay. Okay, so I will wait for you and try it. Hello? Anyone get any answer? If you're trying something and you are having difficulty while doing that, you can ask in steps. Debaru,
Yes, sir.
yeah, are you able to solve?
No, sir, not fully.
Okay, so where's the difficulty? Hello,
Yes, sir.
where is the what's the difficulty?
Sir, the difficulty like lies within that. I'm a bit like not like I'm being a bit unaccustomed to the like data and finding some difficulty to solve that.
Okay,
Am I audible, sir?
yeah.
Uh, so that's where the problem occurred to me.
So what's the issue you're facing? Debaru, what's the issue?
Yes, sir. I'm having some problem like regarding this. So I told you, sir.
Regarding what? I didn't understand.
Like when while I was solving,
Mhm.
so like the data is given in such a manner, I was trying to solve using the equations. So some problem occurred to me.
Okay, just try it. Then I will be going to discuss. So we'll discuss it. We have this secret relationship. So that is G2 tau is equals to 1 plus, so we know this is 1 and this is G1 tau square, and G1 tau is a function of minus d q square t plus b. But it's up to us. We can assume this form in this way also. So q1 can be assumed as a e to the power minus d q square tau. And so if you substitute this here, then G2 comes out to be 1 plus a e to the power minus d 2 q square tau. So G2 tau minus 1 divided by, so this should be equals to a e to the power minus d 2 q square tau. So we have this and we have this. So we can take ln. So ln of G2 tau minus 1 is equals to ln a minus d q square tau. Okay. So we have a set of values. So what we can do is, if you are using Excel or simply what we can do is, let's say this is first value, this is second value. So then ln G2 tau second minus 1 minus ln G2 tau. So that is first value minus 1 divided by 2 times of q square tau. So this data of second value minus q square tau, that is given already, that is of first value. So this is not a square, this is second value and first value. So from here we can get diffusivity. What is the diffusivity? Okay. So for the first value, if we have it for, let's say, 0.
Sir, here I was having the problem. That's why
Yeah.
I told you. So
What?
sir, here, like that you were asking now. So like here I was having the problem.
In calculating this?
Yeah.
Yeah, what's the issue?
No, sir, it's now resolved. Like
Okay. So what's the issue? Like, if you tell, we can discuss it. Maybe others will have any.
no, some calculation error. Like I have fixed it, sir.
Okay.
Yeah. Like while changing that exponential into log, I was having some issue. So no. So it's resolved.
Okay. So we have this value. If we this for the first one, we have the value is minus 0.2876 minus this one I have calculated to be 0.35. So that becomes plus 66. Okay, then this should be divided by twice of 1.7 minus 1.75. Correct? Correct, Debaru?
Yes, sir.
So D1. So we will be getting a number of diffusivity. So from here we will be going to get that is 0.17248. Is it correct? Are you getting it?
Yes, sir.
Okay.
Yes, sir.
Okay. So you can do this in Excel. And so we need to find out the average of D1, D2, D3, and so on. So can you, so are you doing it by hand or what, Devaru?
Sir, hand.
Okay. Dipanvita, have you tried it this way?
Sir, I was getting a constant term over here. ln G2 tau minus 1 equals to ln A minus 2 D2 QT plus I was getting a constant term here. That's why I wasn't able to do it.
Yeah, you can ignore that constant term. So that's what I'm saying, so you can take any functional form because if you try to fit it a curve also, then you will see that this will not going to affect. And this constant term, yeah, that will be not going to affect. So you
Okay.
can assume any functional form of this way. So the functional form is important.
Okay, sir.
Because if you take ln of this also, then how can you separate these two? So you can ignore it. So I can also write it here so that we may also take. So there should be some reason. I will try to find out that there is a way to write this. It's like this, but I didn't find the actual reason, but I'm trying to find it. So in the next class, probably I will be going to tell you that what should be the reason of it. Okay.
Okay, sir.
So diffusivity you can calculate. So once you get the diffusivity,
Yes, sir.
whatever the diffusivity, then we have the hydrodynamic radius from the Stokes-Einstein relation. So hydrodynamic radius, any idea? How can we get it? So that is KT by 6 pi eta D. Okay, so temperature is 27 degrees centigrade is given. Make sure that it should be in Kelvin, so that is 300 degrees centigrade. Then third part is we need to find is hydrodynamic force. So that is nothing but 6 pi mu RH into V. So velocity I am not given. Okay, so velocity for this should be there. The velocity of particle is, this should be there. That is 0.5 micrometer per second. Okay. Then third part is uh, hydrodynamic force on colloidal patch. Sorry, colloidal particle. So that is there. Find the gravity force. So gravity force we have already discussed. That is V, rho Vg. So rho delta rho Vg that is rho of particle minus rho of suspending medium, that is given into 4 by 3 pi. Radius is, you can calculate from here, q into g. Okay, so everything is around this. Then, and the last part is Brownian force. So what is the Brownian force? The Brownian forces KBT by RH, because we don't have any other parameters, so we have to use this. Okay. So from this we can calculate. So now you know all the things. So can you calculate it now?
Yes, sir.
Okay, so try it and I will be giving you answer then.
Okay, sir.
Sir, what is the value of K?
Where this K,
Yes, yes, sir.
so this is the Boltzmann constant.
Okay, sir. Okay.
But first you should find out the diffusivity. This is not, you need to find out the average of the diffusivities. I will be giving you answer shortly. Just try this. It's actually 1.05. So Devaran, did you get other values?
Yes, sir. Calculating.
Yeah, what are the other values? Can you tell? Dipanvita? Kaushika?
Sir, I'm trying to solve.
Okay, so I'm telling you, diffusivity is coming out to be 0.7522 meters square per second. So when you get the diffusivity, you'll get other answer. Devaru,
Yes, sir.
did you get other values of diffusivity like D2, D3?
Yes, sir. I told you like I'm calculating.
Yeah, tell me. What is the second value? Kaushika?
Sir, no, sir. Actually, I'm having some doubts over
Yeah,
there.
yeah. Yeah, tell me.
Sir, here you in that ln minus ln into g square in this formula, this
This
equal
one,
to d1. Next, the
this one,
denominator. Next,
this one. Yeah.
yeah. Here, how? What are the values you substituted there, and you got this value, sir? Because I'm trying of substituting, and I can't get this one. That's why.
So G2 tau is the second value, that is this one 1.7.
Okay.
This
Okay, sir.
one,
Okay, sir.
Okay.
I did mistakenly. That's why
No.
I was thinking for a long. Okay, thank you.
Okay. Okay.
Sir, can you please turn to the previous page?
What?
Can you please turn to the previous page?
Yeah, this one.
Yep.
Okay.
Sir, how to find out q square tau?
So that is there, na Q. Sorry, it's one minute, check. Yeah, it's actually Q square tau. Sorry, it's not Q tau square. This is given.
And but it is given q square tau into 10 to the power minus 10.
Yeah, correct.
So how can we convert it?
Yeah, so it's 0.2 into 10 to the power 10. That is Q square tau.
Okay, sir. So next D value is 0.039.
No, it's 0.8411. What you are doing is this minus this.
Sir, I'm doing
Sir, here though in the second thing, we will like ln 0.6 minus ln 0.6 minus 1 minus ln 0.4 minus 1 by ln 1.5 minus 1.7, right, sir?
Yeah, correct. No. Second one is just like 1.7 minus ln of
Sorry, sir. 2 into 1.5 minus 1.7, right, sir? Like you're just
no second.
from the next
Yeah,
succeeding
correct.
value you are subtracting.
Yeah.
So
Yeah.
yeah, like that
Oh.
only.
Yeah. What is the value?
Sir, 0.8 approximately.
0.8411.
Yeah, I'm getting 83, sir. Some calculation error. Yeah.
So this B is usually some instrument constant. So that you can find. So what I found is that with the discussion with the so B is some instrument constant actually. So here you can take this B to be 0. And for more discussion on this on this B is that is given in a review paper by Hassan in language. I will briefly discuss about it in the next discussion. Then we'll discuss it. Okay.
Like, is it related to language adsorption, isotherm, and
Actually, I don't know that, but no, language is the name of the genre.
okay. All right, sir. All right.
So diffusivity is essentially coming out to be this. So you can try this. Let's say it. So you can try this, and we'll discuss in the next week if you are unable to give it. And you can try this at home, and we'll discuss it.
All right, sir. Thank you.
Okay. Kaushika.
Yes, sir. Yes, sir.
Did you get it?
Yes, sir. Actually, yeah, at starting I did one mistake, so just now I'm doing it. I will do
So
it.
patiently do this, and we'll discuss if you have some doubt in the next discussion.
Okay.
Okay.
Sir, and then actually, I'm not a chemical engineering student. It is little difficult for me. Can you suggest that is there any more numerical problems like any book or any website?
Yeah, the textbook used is that as I discusses Rajgopalan on colloids. Hunter is there, Berg is there, but not. I don't know if these kind of numericals are there.
Okay.
But these are the very usual things. So you are from which background you are?
I'm from physics.
Okay. From which institute?
So which?
Which institute?
VIT,
No.
Vellore Institute of Technology. Yeah.
Okay. Yeah, so that is a book by Rajgopalan is one of the textbooks on colloids, and so you can go through it. This is just a simple thing, and you will find any and numbers of numericals and many other books on this. Uh, this is normal. Um, this is very. So you are undergraduate or postgraduate?
No, sir. Actually, I joined PhD student. Actually, this is how to say it's full of theory, right? While sir was teaching, so so some numerical questions. It's little hard to connect with that thing and go for
So
it. That's
now I have discussed. So with this, you will be all the assignment problems also.
okay, sir.
Okay.
Thank you. Thank you.
Thank you.
Thank you, sir.
Okay. Bye.
Bye, sir.
You will leave. No.